So, good morning everyone. So, last class we were discussing Kravchenko's theorem. So, let me state the theorem from that we saw last time. So, this is a theorem which is used to give a lower bound on functions. Okay. So, what does this theorem say? So, the theorem says that suppose if you have a Boolean function f. Okay. So, let f be a function from zero 1 to the power n to 0 1. So, f is a Boolean function and let A be a subset of f inverse 0 and B be a subset of f inverse 1. So, basically A is some set of inputs which map to 0 and B is some set of inputs which map to 1. Then what we have is that the size of the star size of the function f over the basis and or and not is at least what was the quantity n a b whole square divided by the cardinality of A times the cardinality of B. This is what we stated last time. So, let us try to understand this once more. So, what we are saying is that NAB is basically the number of tuples, okay, from A cross B. Okay, so, the first element of the tuple is from A, the second element of the tuple is from B. So, the number of tuples of the form let us say sigma comma tau such that the Hamming distance between sigma and tau is exactly 1. Okay. So, basically intuitively these are like two strings which are almost the same except for one bit, they differ exactly in one bit. And what this theorem says is that if we have a function f and if we take any two sets A and B such that A maps to 0 and B maps to 1, then this size of the function, the star size means that the number of AND and OR gates. Okay. So, when we say star size we are counting how many AND and OR gates are there and L is the formula. Okay. So, L is the size of the formula for f. So, the smallest formula if I count the number of AND and OR gates for f will have size at least this much. Okay. So, how do we prove this theorem? So, any questions? Okay. So, let us try to yes, exactly. And for any, not just all the input strings, but if I take any subset A and B of the input strings, if they are similar, what that means that NAAB will be larger, which means that they will require larger formula. Yes. So, that is the intuition. So, how do we prove this? So, what we will prove, as I said last time, is basically we will prove about the leaf size. So, we will show that the we will show that the leaf size of f is at most this quantity. So, what is leaf size? Leaf size is the number of leaves in a formula. And why does this, why is this sufficient? Because we know that if we have any tree, if we have any binary tree, then the number of leaves is one more than the, actually the result is this is equal to this minus 1, this is the precise result. And the number of leaves is basically one more than the number of internal nodes. That is why it is enough to show it for the leaves. Okay. So, the proof is by induction on the size of phi. Okay. Let me write it over here. We will prove by induction on phi. So, firstly base case. So, the base case is when let us say phi is a some single variable xi, okay. It does not have any gates. So, then what does this mean? Now, what this means is that if I take any sigma from A, okay. So, suppose if I take any sigma belonging to A, okay, then what is, how large can n A be? I mean, how large can this n A comma B be? Okay. So, if sigma is in A, then observe that, well, look at the variable xi belonging to sigma. Okay. So, look at that position. Okay. So, that is the only position which can change. So, if sigma belongs to A means that sigma is mapped to 0, right. Now, if I want to consider sigma, I mean if I want to consider another input which goes to 1, which differs only in one position from sigma, that can only be at the position xi, because that is the only thing which is affecting the input, right. So, if sigma belongs to A, then the n A comma B will be equal to n A comma B is in fact one second, is at most the size of A. Okay. So, as I said, since sigma has at most one neighbor in B. Okay. And by the same argument, we can say that n A B is at most the size of B. So, now if n A B is at most size of A and B, therefore, the result clearly follows. Okay. Now, let us look at the induction case. So, the induction case we will divide it into 3 parts. Okay. So, the first part is when, suppose let us say phi is equal to naught of some formula psi. Okay. So, if phi is naught of psi, now let us consider the possibilities. So, suppose if I have a set A which is a subset of phi inverse 0, what can I say about A with respect to psi? So, A is basically a set of inputs which go to 0 in this formula phi, right. So, with respect to psi, it would go to 1, right. So, if A is a subset of this, it implies that A is a subset of psi inverse 1. Okay. And similarly, if I have B which is a subset of phi inverse 1, it implies that B is a subset of psi inverse 0, and this is if and only if. Okay. The same thing holds for the opposite direction as well. So, therefore, this proves the and now psi is a smaller formula because it has one less gate. Okay. Therefore, by induction I know that the formula is true for psi, hence we are done. So, if I have a formula which is not of some other formula, then it follows by this observation. Okay. Now, let us look at the more interesting case when suppose phi is equal to and of something. Okay. So, let us say it is, sorry, let me just write it a little lower. Phi is equal to psi and some formula chi. Okay. So, if this is the case, let us try to rewrite this. So, suppose if I have A, which is a subset of phi inverse 0, okay, which means that all inputs in A map to 0, then what do we have? That A is a subset of. So, what can I say about A with respect to psi and chi? Psi inverse 0 . So, suppose if I have an input, so what does the AND mean? So, if I have a 0 over here or a 0 over here, it is a 0 over here, right. So, if one of these two go to 0, then it will go to 0. So, it will be union, not intersection. Okay. So, if either psi maps to 0, I mean if I have an input which is mapped to 0 by either psi or by chi, then I know that phi will map it to 0 and hence it would belong to A. Okay. Now, if I take B such that phi, which is a subset of phi inverse 1, what can I say about B over here? So, when is an input mapped to 1? So, if I have an if both of them are 1, right. So, what should it be? So, it will be phi inverse 1 intersection with chi inverse 1. Once again, this is if and only if, right. So, if either of them goes to 0, then this would go to 0, and if both of them go to 1, this will be 1, right. So, now we know how to divide. So, we know how to kind of state an input in terms of the sub formula over here. So, now let us try to let us just establish some notation before we proceed. So, let so what notation do I have? So, let A of phi be a subset of phi inverse 0 and A of chi be a subset of chi inverse 0 such that if phi intersection with A chi is disjoint, okay, they do not have any common element, and if psi union with A chi is my set A. So, all I am saying is that I take A and I just divide it, I just partition it into two parts, A psi and A chi, okay, where A psi is basically all those inputs which takes psi to 0, and A chi is all those inputs which take chi to 0. Now, there can be some common elements in between. Okay. So, there can be some inputs which take both psi and chi to 0. I can put them in either one. I can decide to put it in either one, it does not matter, but I just want to ensure that there are no common elements. Okay. This is any partition, and I will also use another notation. I will use n psi to be n of A psi comma b and n chi to be equal to n of A chi comma b. Okay. Now, how many neighbors or how many triplets are there which are neighbors between A chi and b, and how many triplets or how many tuples are there which are neighbors between A chi and b, right. So, what is the relation between n A b and n psi and n chi? So, what was n A b? n A b is all those tuples such that the first element belongs to A and the second element belongs to B, and they are neighbors. Now, I am partitioning A into A psi and A chi, right. So, what would be the relation? Exactly. So, n A b is nothing but n psi plus n chi, right, because each tuple I can decide to put it either in this set or in this set, okay, each tuple belonging over here. Okay. So, now we have established the notation, now we can get to the proof. So, what do we want to prove? We want to prove that leaf size of chi sorry, leaf size of phi is greater than this. So, let us take this. So, leaf size of phi. So, phi is a formula which means it is a tree, and how does the formula look like? The formula has an AND gate at the top, and there are two sub formula, right, psi and chi. Okay. So, what can I say about the leaf size of phi in terms of the leaf size of psi and chi? It is just the addition, it is the total number of leaves, right. The total number of leaves in the entire tree is the number of leaves in this subtree and this subtree. So, it is equal to leaf size of psi plus leaf size of chi, and by induction what we have is that this quantity is greater than or equal to, now I can use my notations, n psi square divided by A psi times b plus n chi square divided by A chi times b. Okay. So, this follows by induction. Now, let us try to expand this out. So, because I just decided to split it in terms of A, that is all. I am just taking this and I am just deciding to split it in terms of A over here, that is why B remains same. So, I had a notation, I think. So, let me just so that it becomes a little simpler, let me just keep one more notation over here. Let small a of psi be size of this set, and small a chi be size of this. Okay. So, therefore, I can write this as small a psi times small a chi. Okay. So, if if we expand this out, we get n psi square a chi plus n chi square a psi divided by size of b times a psi times a chi, and let me also multiply both numerator and denominator with a psi plus a chi. Okay. And once again we expand this out, we expand the numerator. So, if we expand the numerator, we get n psi square a psi a chi plus n chi square a psi a chi plus n psi square a chi square plus n chi square a psi square whole divided by b a psi a chi a psi plus a chi. Okay. Now, look at this term over here. Okay. Look at this particular term over here. Okay. So, what can I say about this term? So, what we can say is that this term is actually greater than or equal to twice n psi n chi a psi a chi. How does this hold? Huh? Exactly. Okay. So, I can take this as, let us say, a term x, and I take consider this as my term y. So, x minus y whole square is nothing but this minus this, and x minus whole square is always greater than or equal to 0. Okay. So, using that inequality we get this result. So, now I can write this as this quantity is greater than or equal to okay, fine, let me write this out, n psi square a psi a chi plus n chi square a psi a chi plus twice n psi n chi a psi a chi divided by b okay. Now, I take a psi a chi as common, and what I get is n psi plus n chi whole square divided by b times a psi plus a chi, and this is nothing but we can just substitute n a b square divided by this is a and this is b. So, A times B. Okay. So, this completes the proof. And now, what happens if we have OR over here instead of AND? So, if I have OR over here, so instead of union over here, I will have intersection, here I will have union, and I can decide to partition B instead, and I get the same argument. Okay. So, case 3, if phi is equal to psi or chi, similar argument holds. Okay. So, this completes the proof. Now, why is this theorem interesting? How does it give a lower bound on the formula size? So, let us take an example. Let us consider a couple of applications of this theorem. So, the first application. So, any questions about the theorem or its proof? So, one very crucial point about this theorem is that this theorem only gives a lower bound on a function over the De Morgan's basis. Okay, so, this is very crucial. So, when we are using this inductive argument, okay, we are very crucially using that the gates that are present are just AND, OR and NOT gates, and in fact, we are not even counting the NOT gates. NOT gates can be arbitrary, but we are counting just the AND and OR gates in that circuit. Over any other basis, this theorem will not hold. Okay. So, and we will come to this point a little bit later. So, let us consider a function, let us consider the parity function. So, consider parity of x1 up to xn. Okay. So, how is the parity function? Let me just define it once again. So, parity of x1 to xn is equal to 1 if sigma xi is congruent to 1 mod 2 and it is equal to 0 otherwise. Okay. So, how can I give a lower bound on the formula size of the parity function using Kravchenko's theorem? So, to give a lower bound, I have to suitably choose A and B. Okay, I have to suitably choose A and B, and now once I have chosen A and B, I can use the theorem. Okay. So, what I will choose is that, so let A be, in fact, I will choose A to be all inputs which map to 0, sigma in 0 1 to the power n such that parity of sigma maps to 0, and I will choose B to be all inputs in the same domain which map to 1. Okay. So, what can I say about the size of A? How many inputs go to 0? Huh? 2 to the n minus 1. Okay. So, there are 2 to the power n many inputs, half of them go to 0, half of them go to 1, right. So, okay. So, this thing is settled. Now, what can I say about n a comma b? How many tuples are there which are neighbors? So, how do you answer? I mean, how do you think? So, if for any set a comma b, if let us say someone poses this question, how do you think about it? Okay. So, the way you should think is that consider any string, let us say in A. Okay. How many neighbors will that string have which belong to B? Okay. So, let sigma belong to A. How many neighbors will it have which belong to B? N, because I can take any bit of sigma, and if I flip that bit, the parity changes, and because the parity changes, it goes to B. So let sigma in A, the number of neighbors of sigma in B is n. So, therefore, what can I say about, and this is basically true for each sigma, okay, for each sigma this is true, each sigma in A. So, therefore, NAB is equal to size of A times n, and I can give the same result for B as well. I mean, anyway, A size of A and B are the same. So, therefore, it follows. So, now what does Kravchenko's theorem give us? So, by Kravchenko, they need not be different, they can be the same. You mean the B's? I am looking at tuples. The tuple is different, right. So, it is all pairs sigma comma tau. So, I am fixing a sigma for which I have n many taus. Now, there are 2 to the power n minus 1 many sigmas, right. Of course, some of those taus will repeat, but the sigma is different. This is greater than n times A, n times, I can write it as B divided by A times B, which is equal to n square. Okay. So, this says that if we look at the parity function, we need a formula of size at least n square over AND OR and NOT gates for this formula, okay, for this function. Now, let us look at another example. Another famous function is the majority function. So, majority of x1 to xn is equal to 1 if sigma xi is greater than or equal to n by 2 and it is equal to 0 otherwise. So, if at least, I mean if the sum is at least n by 2, then the input is mapped to 1, otherwise it is mapped to 0. So, what can we say about the formula size of majority? Now, how do we choose A and B? Okay, so, actually if you choose A and B nicely, then the problem is almost solved. Okay. So, how do you choose A and B? Any guesses? So, the idea is you have to choose A and B in such a way, so that this if I look at NAB, that is if I look at these tuples, that quantity should be maximized. Okay. I mean I have to choose A and B. Okay. So, that is the idea. So, and how do you maximize NAB? It is when you have an A and shifting just one bit of A or flipping just one bit of A would send it to B, right. So, what would such an A be in this case? So, just less than half many ones, right. So, A is something which should go to 0. So, if I have n by 2 minus 1 many ones in that string, then flipping 1 0 to a 1 would send it to B, correct. And what should B be? N by? No, B will be exactly n by 2 many ones, right, because just changing 1 1 to a 0 would send it to A. Okay. So, it is kind of so these two sets are like on the borderline. Okay. So, changing one bit of A string from A sending it to B, and from B changing one bit to 0 would send it to A. Okay. So, these are kind of like the borderline sets. So, that is the intuition, that is how these sets should be thought about. Okay. So, I mean it might seem like it is kind of, I mean initially it might seem like magic that how these sets are picked, but I mean once you understand what is going on, it is quite intuitive as to how these sets should be picked. Okay. So, we will pick A to be all strings over here such that sigma has n by 2 minus 1 many ones. Okay. So, if it has n by 2 minus 1 many ones, clearly it is mapped to 0, and that is what we have, and B is all, let us say tau n 0 1 to the power n such that tau has n by 2 many 1. If it has half many ones, then by definition it is mapped to 1, correct. Now, let us count the, sorry, this is B. Okay. Now, let us count NAB. So, for a sigma belonging to A, okay, how many neighbors does it have which belong to B? We can make any of the zeros. So, if I flip any of the 0 to a 1, then it becomes an element of B. How many 0 does sigma have? N by 2 plus 1. If it has n by 2 minus 1 ones, then it has n by 2 plus 1 many zeros. So, for a sigma belonging to A, it has n by 2 plus 1 neighbors in B. Okay. I can take any of the zeros and flip it to 1, and for tau belonging to B, how many neighbors does it have in A? N by 2, because any of the zeros I can, sorry, any of the ones I can make it into a 0 and it would go to A. It has n by 2 neighbors in A. Okay. So, can you guess what the lower bound would be? What is the lower bound? So, NAB is equal to A times n by 2 plus 1, also it is equal to B times n by 2. So, therefore, L star of majority is greater than n square by 4. So, it is greater than n by 2 plus 1 into n by 2, which is greater than n square by 4. So, this is a lower bound on the formula size. So, similarly, many other functions, for many other functions you can give a lower bound using this formula. So, any questions? Higher than polynomial lower bound, not that I know. For a fixed A, yeah. So, once you fix an element in A or B, it can have only a maximum of n neighbors. So, getting better than quadratic is not possible. Yeah. Correct. Okay. Yeah, that's a good point. Okay. So, now what happens if we consider arbitrary basis? Okay. So, here as I said that Kravchenko's theorem crucially depends on the fact that the basis is the De Morgan's basis. Now, what happens if we go to let us say B2? Okay. So, how can we give a lower bound on the formula size of a function over B2? So, this brings us to another very interesting result. Okay. So, this result was due to a Russian mathematician Nechiporak, and he showed that you can actually consider, I mean you can actually give similar type of lower bound for even arbitrary basis. Okay. So, here we will just prove it for B2, but if you just think about it, it can be extended to any B k for that matter. Okay. So, just to recall, so B2 is the basis of all functions over 2 inputs. Okay. So, B2 will have a total of 16 gates. So, before getting into Nechiporak's theorem, we have to define a few things. Okay. So, it needs some background work. Okay. So, we have to define this concept of restriction, okay, restriction of a function, and this restriction of a function is going to be very important as we move in this course, okay, because there are other topics that we would be discussing later on, and they would crucially depend they would crucially depend on this idea of restriction. Okay. So, let me define what we mean by restriction of a function. So, let f be a function from 0 1 to the power n to 0 1. Okay. So, before proceeding with the definition of restriction, so the definition is mathematically it might seem a little complicated, but let me give you the idea. So, the idea is very simple. So, I have a function on n variables, right. Now, suppose if I decide to fix some of the variables. Okay. So, between these n, let us say I pick some subset of the variables and I say that okay, these fixed variables will go to some fixed inputs. Okay. So, they will go to, some of them will go to 0, some of them will go to 1, and only the remaining variables are free, in the sense that they are actually variables, they can actually take a value either 0 or a 1, and depending on that the function is evaluated. Okay. So, that is what is called a restriction. Okay. So, we take a subset of the variables and we map them to either 0 or 1, and only the remaining variables are free. Essentially, that is the idea of a restriction. So, let f be a function on n variables over, let us say, the variable set x. So, I am just giving a name to the input variable set x 1 up to x n. Okay. Let y, which is equal to y 1 up to y l be a subset of x. So, each of these y i's are some x j's over here, okay, and I have some l many of them. So, the idea is that these y many or this set y will remain free, and the remainder I will fix them. Okay. Now, let z be equal to x minus y. So, this is the z that I will be fixing, a restriction second, let me see what is the terminology, sigma from z to 0 1 is the function. So, I will call it f sigma on the variable set y 1 up to y l, which is f of x k 1 up to x k n, such that if x k I is equal to y j, or j if x k I is the jth element of y, and x k I is equal to sigma x I if x I is not in y, basically if it belongs to z. Okay. So, essentially I look at all the variables now. Okay. So, among all the variables, if I have a variable which belongs to the set y, okay, then basically it is I mean it is just a free variable, and if it belongs to the set z, then I will set it to sigma of that quantity. Okay. So, this restriction which is mapping this set z to 0 or 1. Okay. Now, what? No, 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 this is y l. Yeah, this is y of l. It is restriction, this is a notation for restriction. So, f restricted to sigma, this means. So, basically the idea is that f behaves exactly the same, f restricted to sigma behaves exactly the same as f on the inputs of y, and on the inputs which are not in y, that is the inputs which are in z, it takes the value sigma of this. Okay. That is again the idea. Now, what else do I have to define? Okay. A sub function f restricted to some sigma is any function with domain of sigma being x minus y. Okay. A sub function on y f sigma. Okay. So, basically what this is saying is that if I take any y, so any sub function on y is basically a function sigma on this domain x, on the domain x minus y. Okay. So, now we can state the theorem. So, what let me check if we need, let so let f be a function from 0 1 to the power n to 0 1, okay, and let y 1 up to y k be disjoint subsets of the domain x x1 up to xn. Okay. Then L over B2 of f is greater than or equal to 1 plus 1/4 sigma log of Si, I going from 1 to k, where Si is the number of distinct subfunctions of f on y I. Okay. So, let us try to understand what is going on. So, we take a function f and we look at its domain and we just consider subsets of the domain that are disjoint, okay, some y1 to yk. Okay. So, basically this is basically just collection of the variables x1 up to xn such that no two subsets have a variable in common, but it need not be a partition in the sense that it need not contain all the variables. I am not saying it is a partition, just these are subsets. Now, what we are saying is that if over all these domains, okay, so let Si be the number of distinct subfunctions. Okay, so here what I define what a subfunction is. So, on a subset y, okay, a subfunction is basically any restriction. Now, I can have many types of restrictions on the same subset, okay, depending on how I fix sigma. So, for various different sigmas, I will have various different subfunctions, and Si is the total number of distinct subfunctions of f on yi. Then what we are saying is that the lower bound of f over the basis b2 is 1 plus 1/4 of log of Si. Okay. So, as the number of subfunctions keep growing, the lower bound will increase. Okay. So, again this is kind of intuitive, because what it says is that, well, if we have a function such that for any restriction it has many different subfunctions, then the function should be complex, okay, which means that it should have a higher formula size, and that is what it kind of means. Okay. So, any questions about what we mean by a restriction or what this theorem states? That is the definition. So, sigma, the domain of sigma is z, okay. Z is defined to be x minus y. So, what we are saying is that a subfunction on y, so if I fix y, now a subfunction on y is basically any function whose domain is z, that is what we are saying. Okay. So, if I fix sigma to be some z, okay, which is sending some elements to 0, some element to 1, then my subfunction is fixed, but depending on what sigma is, I can have many different subfunctions.
The definition should be like given sigma, the restriction is the function. Isn't that
Which definition are you talking about? Yes, given sigma, yes, a restriction, this is, so basically here I am defining a restriction. So, a restriction is a function sigma on z. Okay. So, given a function f and a set y, a restriction is function sigma on x minus y, which is sending, yeah, it's a Boolean function on x minus y, which is defined in this manner. Now, how many different restrictions are there? That is basically the number of subfunctions.
what you are referring to as a restriction is that function sigma.
Yes.
Then the number of subfunctions and number of restrictions are different. They are two different ones.
Well, I mean,
So, if a sigma is what you are calling as a restriction,
yes,
the number of restrictions is just the number of functions from set to zero.
yeah,
But then the subfunctions number of subfunctions can be much more.
it can be more, yes, it can be more. Yeah.
Why the number of subfunctions can be the same, right? It can be different. Two different functions are using their big functions.
Well, no, it cannot be more, it can be less actually. It can be less because two different sub functions can be the same over here. Yeah.
Also, in this theorem, disjoint subsets is considered, but not a partition.
No.
But
This is just making the theorem stronger, right? I mean, you can have a partition also, but you need not have a partition.
let's say it's not disjoint.
No, if it is not disjoint, then the theorem will not work. So, the proof, when we look at the proof, you will see that it crucially relies on the fact that the set of variables are not common. The set of variables of yi's, they are not common.
So even if this y1 to yk are missing certain elements,
That is okay.
by adding them we can actually strengthen the theorem.
We can, no, we are weakening the theorem, right? Because partition is a more stronger, so this is
That's
basic.
okay, fine. But if we add the remaining elements as another y k
Yeah.
plus 1, the lower bound will go up.
It, no, the lower bound will stay the same.
But there will be another SI term in the summation.
Yeah, okay. So you are saying that you add one more set which has the remaining element. Yeah, so then yeah, so then you will have some other SI term. But this is like a more general version, right? So this will work even when you do not consider all the variables.
Then there will be k plus 1 many sets, and then the theorem statement will have
K plus 1, huh?
So it's still the
Yeah. Okay. Okay, so let me talk about the proof. Actually, the proof is not very difficult. So once this setup is there and once you understand what a function and its subfunction is, the proof is just a couple of observations. So let Li be the number of occurrences of variables in yi in a formula for phi. Okay. So, consider a formula for phi, any formula, and let number of occurrences of variables. So, now the variables of any formula are always the leaves, right. So, I am only looking at those leaves variables in yi. Okay. I am only looking at those leaves which are the variables from the set yi, okay. And I am going to count this Li. What I will show is that Li is greater than or equal to 1/4 log Si. Okay. So, this is what we will show. Now, why is this sufficient? So, basically if I show this for Li, now if I sum all the Li's, that is basically the total number of leaves in the tree. So, that will show that the total number of leaves is greater than the quantity on the right hand side, and the total number of leaves is basically half the size of the entire formula, right, because it is a tree. Therefore, the size of the formula is nothing but the number of leaves. In fact, the number of leaves is one more, that is why we have this 1 over here. So, the number of gates is 1 less than the number of leaves. I am just counting the number of leaves over here. Okay. So, clear so far? Okay. Now, how do we prove this quantity? So, to prove this quantity, let me just kind of give the intuition pictorially. So, consider the formula, the entire formula phi. Okay. So, let us say this is my entire formula phi, and let us say that there are certain inputs which belong to variables in yi. Okay. So, let us say this is some input which is belonging to yi, this is another input belonging to yi, and there are certain inputs which do not belong to yi. Okay. Now, look at all the paths from the leaves which belong to yi up to the root node. Okay. Suppose this is a path which goes from a leaf to the root node. This is another path which is going to the root node. Here I have maybe some other path. Okay. It's a binary tree, so okay. And I can also have, let us say, some other node which has a path to a leaf which is not in Y, okay, but we will not be considering these things. So, these are nodes that I will not consider, but these are the paths that I will not consider. So, here I am only considering the purple paths. Okay. Now, how many leaves are there? So, the number of leaves is, so the number of leaves is equal to Li, and the number of nodes with 2 inputs will be how many? So, this is, I am only considering the restriction. Okay. So, let me just state this over here. So, consider the restriction of the formula to input gates that belong to yi. Okay. So, I am considering the restriction of this formula to the input gates which belong to yi, and in this formula I am counting how many leaves are there, Li, how many nodes are there which have 2 inputs. So, again it is a sub formula. Okay. So, which means that it has a tree structure. So, if I have a tree which has Li leaves, how many nodes are there of degree 2 in degree 2? It is a binary tree. Well, it need not be a binary tree. I mean, I can have a path over here where some of these nodes can have in degree and out degree 1. But if I look at the nodes which have in degree 2, how many nodes will there be? Huh? What? So, again this is, you can go back and look at this. So, this is from the theory of binary trees. The number of nodes of in degree 2 will be Li minus 1. Okay. So, one way to look at it is that if you compress all these paths, okay, so we have these paths that are present. So, if I compress all these paths and make it into a make it into a binary tree, that is every node has in degree either 0 or 2, then we know that the number of nodes of the number of internal nodes is Li minus 1, 1 less than the number of leaves. But even if I stretch them and make them into paths, it is basically each node has in degree and out degree 1. So, they are kind of cancelling out. So, the number of nodes of with 2 inputs, that is in degree 2, will be equal to exactly Li minus 1. Okay. Now, what we will do is we will consider all these paths. Okay. So, consider all paths from a leaf node. So, let me call this set as x, say xi. So, all these nodes which have or net x is already used, let me use w. So, all these nodes with 2 inputs, let me call them as wi. So, consider all paths from a leaf node to a node in wi or from a node in wi to the next node. Essentially what I am saying is, look at all these paths. Okay. So, here I have a path from a leaf node to a node in wi. So, this is one path. Here I have another path, second. Here I have another path from here to here, third, fourth, fifth, sixth and seventh over here. Okay. So, look at all these paths that are present in this subtree. Okay. How many such paths are there? So, corresponding to each leaf and corresponding to each node in wi, I will have one path, okay, which is basically the path going from that node to the next node above it, correct. So, the total number of such paths is equal to 2 li minus 1. And what is each path? Okay, so, each path is basically a function on one variable, in the sense that each path takes a value and it is either outputting that same value or it is outputting the negation of that value or it is outputting 1 or it is outputting 0, right, each such path. So, each such path is a function on one variable. There are 4 functions on one variable, 4 such functions. So, I can have h of x as being equal to x, I can have h of x as not of x, I can have h of x equal to 0 or h of x equal to 1. So, these are the only 4 possibilities for these functions and for these paths. And now, any sub function, so a sub function is basically just this subtree, any sub function is uniquely determined by these all these paths. So, once I fix all these paths, that uniquely determines a function. So, therefore, each sub function is determined by these paths. Therefore, the number of sub functions is at most 4 to the power 2 li minus 1. So, which is equal to 2 to the power 4 li. I mean, I can just leave out this 1, which implies that if I take log on both sides, I get that li is greater than or equal to so 4 li is greater than or equal to log si. So, li is greater than or equal to 1/4 log si. Okay. So, that completes the proof.
Any choice of values along the path will not give us a function, right? Some of them may be nonsense.
Some of them may be nonsense, yeah. So, that is why I have, it is an upper bound on this. Yeah. Okay, so, I will stop here. So, we will come back to this. So, again next class we will come back to this theorem, we will understand this theorem little more in depth, and then what is more important is we will look at applications, how we can apply this theorem to get lower bounds for various functions. Okay, thank you.